in childhood we all must have played with magnets. We might have played a safety pin over a paper and the magnet below the paper and made the safety pin move by moving the magnet. It's just not me and you, even great scientist Albert Einstein had some childhood memory about the magnet. He was gifted with a magnet by one of his relatives and he played with it endlessly. He actually has wondered how that magnet was able to attract small nails, safety pins, etc., though they are not connected by string or spring. So from this what we understand is that magnet always attracts small pieces of nails, iron objects, safety pins, etc. And later it was found that magnet, when suspended freely, it aligns along north-south directions. Even this property was used by our ancestors, especially navigators, to find the directions. They used that suspended piece of magnet to identify the directions and lead their ships. That is why it is known as lead stone. Later it is known as lodestone. So magnet is one which fundamentally shows two properties. Magnet shows attractive property. That means it attracts small pieces of iron, cobalt, nickel, steel, etc. Attracts small pieces of iron, cobalt, nickel, steel, etc. And also it shows directive property. That is, when a magnet is suspended freely, it aligns along north-south directions. Aligns along north-south directions. Why would it align along north-south directions? Why would it attract small pieces of iron, cobalt, nickel? We'll discuss after theories of magnetism. Till then, we shall accept that anything which shows these two properties is called a magnet. And based on the shape, there are different types of magnets that we come across. One is horseshoe magnet. It is in this shape. The other is bar magnet and magnetic needle, etc. When this magnet is dipped in iron filings and taken out, the iron filings cling to the magnet near its ends. Similarly here. So from this we can understand that the magnetism of a magnet is mostly concentrated at points near the ends here. So these points near the ends where the magnetism of the magnet is assumed to be concentrated are called as magnetic poles. Magnetic poles. We see for every magnet that I have mentioned, either bar magnet or horseshoe magnet or magnetic needle, as the iron filings are clinging to the it at the nearer the ends, we can say there are two poles for each magnet, for any magnet. Now already we learned that when it is suspended freely, it aligns along north-south directions. So the tip of the magnet that is pointing towards geographical north is called the north pole of the magnet, and the tip of the magnet that is pointing towards the geographical south is called as south pole of the magnet. That is, if you see that this is geographical north, south, west, east, this is how we indicate the directions. And when a magnetic needle or a magnet, bar magnet, is suspended freely, it will align like this. So this end of the magnet pointing towards geographical north is by convention called as north pole of the magnet, and this end of the magnet or this tip of the magnet pointing towards geographical south is called as south pole of the magnet. So from this we can understand that a magnet consists of two poles. If you consider a bar magnet like this is north pole, say this is south pole, this is for horseshoe magnet north pole, south pole, and this is for magnetic needle north pole, south pole. For convenience of understanding, let us look at bar magnet. If you take a bar magnet, cut this bar magnet, because we have north pole at this end and south pole is at this end. If you cut this magnet into two pieces, then each of this piece again is found to have two poles but of weak magnetic properties. That is, magnetic pole strength or the ability of it to attract the other magnetic pole is not the same for these two. It has weaker properties. Now, if you cut even like this, it is found to have, that is, if you cut like this, we get two pieces, and even these two pieces will have weaker magnetic properties and possess both poles, north pole and south pole. That is, from this what we can understand is that magnet always exists as a dipole. Monopoles do not exist. Like the charged particles, positive charge, negative charge, we cannot have monopoles. Always it exists as a dipole. Now, why is it that this magnet behaves, that is bar magnet or horseshoe magnet or magnetic needle, why does it have magnetic properties like this? Why at one end one north pole is there, at other end south pole is there? To understand it, though it is not included in the +2 level, intermediate level, we will discuss that theory called molecular theory of magnetism. So from this molecular theory of magnetism, whether a magnetic substance, what is that magnetic substance? A substance which attracts magnet, which is attracted by magnet, is called as a magnetic substance. That magnetic substance, whether it is magnetized or not magnetized, it will have molecular magnets. That is, as I told you, if this is a bar magnet, if you cut it into pieces, each piece behaves like a magnet. This is north, south, but with weaker properties, as we discussed. If you go on cutting into smaller pieces, the smallest one which is having the magnetic properties is the molecule of this substance, that is called a molecular magnet. Even that molecular magnet will have magnetic poles. So, if you consider a magnetized substance, these molecular magnets happen to be in an orderly manner. In case of unmagnetized state, that is, if you consider a piece of iron, that piece of iron does have molecules which are magnetic properties, which have magnetic properties. That is, each molecular magnet, each molecule is behaving like a magnet, but in unmagnetized state, these molecular magnets are randomly present, are present in the form of closed chains or loops, so that they cancel their magnetic effects with each other, with one another, so that it will not have any magnetic property. That is, it will not behave like a magnet. But if it is magnetized by any of the methods like single touch method, double touch method, or electromagnetic method, geomagnetic method, any of these methods which you have come across in lower classes, then what happens is these molecular magnets happen to be aligned in an orderly manner. They happen to be aligned like this. Now, here from this point to this point, if you consider, if I say the molecular magnet is denoted by an arrow, if I say that this is north pole, this is south pole, then this north pole, effect of this north pole is balanced by south pole. Like that, all the magnetic poles of these molecular magnets happen to balance each other or cancel each other from here to here. But at this end, the effect of all these south poles get added up, and here also effect of all these north poles get added up. So therefore, effectively this behaves like a south pole and this behaves like north pole. That's what we have observed, that if you take the magnet and dip it in the iron filings and take it out, we see that the magnetic, the iron filings cling to it near its ends. So, if you consider such a magnet which has molecular magnets arranged in an orderly manner, we understand that one end is south pole and this end is north pole. So, the distance between two poles of a magnet is called as magnetic length. Magnetic length is one of the important terms that we have to learn for understanding certain quantities like magnetic moment. So, if it is a bar magnet, for convenience of understanding, we are considering bar magnet. So, this is north pole, this is south pole. So, actually, though I am saying that it is north pole, south pole, not exactly this end is like magnetic north pole. Some point inside is behaving like magnetic north pole. That is, what is understood is that if this is the midpoint, this is north pole, this is south pole, and the distance from here to here is denoted by L's lowercase l, and from here to here is also denoted by lowercase l. That is, the magnetic length of this bar magnet is 2L like this. And experimentally, what is it found is this magnetic length of the bar magnet is found to be less than the geometrical length, that is the length that we measure with the help of a geometrical instrument like scale. It is found to be less than this. Magnetic length is found to be less than the geometrical length, and experimentally this is found to be 2L is equal to 5/6 of the geometrical length. Now, we need to know certain other points about this magnet. As we learned that this point near the end behaves like north pole, and this point near the end behaves like south pole. The distance between these two, north pole and south pole, is called as magnetic length. Now, if you consider this again a bar magnet, this is north pole, this is south pole, this is midpoint. An imaginary line passing through these north and south poles of the magnet is called as axial line. I'm sorry. It is axial line. And an imaginary line passing through the midpoint and perpendicular to the axial line is called equatorial line. Now, once after we knew what is a magnet, that is the one which shows attractive property and directive property, and knowing that it has magnetic poles, that is every magnet has two poles, and magnetic length, that is distance between north and south poles, and also knowing axial and equatorial lines. Now we shall go for pole strength. Let us try to understand pole strength. Though monopoles do not exist, for convenience of understanding theories, we consider monopoles. For example, if this is a magnetic pole, monopole is not existing. Let us say this is north pole of bar magnet. This north pole of the bar magnet, if it happened to be closer to some other magnet like this, obviously it gets repelled or it gets attracted depending on how they are placed. So the ability of it to attract this magnetic pole is measured with the help of a quantity called magnetic pole strength. Magnetic pole strength is usually denoted by a letter lowercase m. And this magnetic pole strength, actually you can talk about even a mathematical formula for this, like a magnetic pole when it is placed in a magnetic field. What is magnetic field? We are going to learn later. It experiences force. That force by formula is F is equal to mb. From this we can define this magnetic pole as the force experienced by a magnetic pole when placed in a magnetic field of unit induction. This magnetic pole is a scalar quantity, okay, and it is denoted by small m as I discussed earlier, and its SI unit happen to be ampere meter. Okay. Now, we understood what is magnetic length and what is magnetic pole strength. Now, we came across a quantity called magnetic moment. Magnetic moment, definition of magnetic moment, we will discuss it from torque experienced by a magnet placed in a magnetic field. But for talking about the strength of the magnet, we need to talk about magnetic moment. So that magnetic moment is equal to magnetic moment of any magnet. It is denoted by capital M. Okay. So it is equal to, magnetic moment is equal to product of, it is not defined as, definition we will come across from torque. So it is equal to product of magnetic length and pole strength. Magnetic length and pole strength. It is something like what you have come across as dipole moment in chemistry. We will discuss even dipole moment in electrostatics. So mathematically it is written as 2L times M. Here this pole strength is a scalar, but magnetic moment is a vector. That means even magnetic length is a vector. The direction of the magnetic length or magnetic moment is taken from south pole to north pole. That is, if you consider this as a bar magnet, this is south pole. If I consider this is north pole, then it is from south pole to north pole. The magnetic moment direction is taken to be from south pole to north pole. And SI unit of this magnetic moment is ampere meter square. So here we need to know certain mathematical relations when different magnets are placed with some orientation. How will the effective magnetic moment can be calculated? We can see. See, for example, if this is a bar magnet of magnetic moment M1, let us say this is south pole, this is north pole, first magnet, this is placed like this. Another bar magnet, if it is placed like this, let us say with their like poles together. Vectorially, this magnetic moment M1 bar can be represented by this arrow from south pole to north pole. This magnetic moment can be represented by this arrow M2 bar. If these happen to be in the making an angle theta, then we can say that this is theta. These two vectors, M1 bar and M2 bar, they happen to be coterminous, and that is what is the angle between the vectors. Hence, we can say net magnetic moment of this arrangement is obtained from parallelogram law of addition of vectors. We already learnt that. So if M1 and M2 happen to be acting at an angle theta, then it is M1 square plus M2 square plus 2 M1 M2 cos theta. Okay. Similarly, if these magnets happen to be arranged with their unlike poles touching, this is one bar magnet S1 N1 of magnetic moment M1 bar, and this is another bar magnet. If S2 is like this, N2 is like this, and the angle between them is theta, then this vector, magnetic moment vector M1 bar is like this, this magnetic moment vector M2 bar is like this, and this is the physical angle that we see, but the angle between the vectors is angle between their directions. Therefore, we have to extend it like this, and if this is theta, this is 180 minus theta. So therefore, we can say the angle between the given magnets placed with their unlike poles touching each other is, that is angle between the magnetic moments is 180 minus theta. So again from parallelogram law of addition of vectors, we can say that the net magnetic moment is given by m1 square plus m2 square plus, actually there is nothing wrong, 2m1 m2 cos of 180 minus theta, and on simplification we get it to be equal to root over m1 square plus m2 square minus 2m1 m2 cos theta. Now, if you have two magnets of magnetic moments m1 and m2, if they happen to be arranged perpendicular to each other, that is, if they are arranged in the form of a cross, n1 s1 n2 s2, or if they are arranged in the form of letter T, or if they are arranged in the form of X, letter X. In all these cases happen to be the magnetic moments oriented at 90 degrees. Okay? So that the net magnetic moment of the arrangement will be equal to m1 square plus m2 square, as theta is equal to 90 degrees and cos theta is equal to 0. Cos theta is cos 90 is 0. Therefore, we get it as m1 square plus m2 square. Now, if it is a bar magnet having pole strengths m each, that is, both the poles of a given bar magnet will have same magnetic pole strength, because the number of magnetic north poles of the molecules or number of magnetic south poles of the molecules are equal usually. That is, if you take a symmetric bar magnet. So as I told you from Ewing's theory of molecular magnetism, these molecular magnets happen to be in an orderly manner. Each molecular magnet is of same pole strength, so they happen to be like this. And this is effectively behaving like north pole, this is effectively behaving like south pole. And such a magnet, if it is cut along its axial line, I told you already that the imaginary line joining the north and south poles is axial line. If you cut this magnet along the axial line, then obviously the area of each magnetic pole is becoming halved. As the area is becoming halved, the number of molecular magnetic poles happen to be halved. Therefore, the pole strength of each piece will be halved. So one important thing that we need to know, that on cutting the magnet parallel to the axial line or along the axial line, the area of the magnet is getting decreased. As the area is decreasing, pole strength is also decreasing. Magnetic pole strength is directly proportional to area of the pole. Because the number of molecular magnetic poles is getting reduced. And in this particular case, this piece having magnetic poles N1, S1, and this piece having magnetic pole strengths N2, S2, if you consider. So as the area is halved, if the magnetic pole strength of this is M, this becomes M by 2. If you cut it along the axial line. And the magnetic length, the distance between the north and south poles, would remain same as 2L in this case, even for this piece. Therefore, the magnetic moment of each piece, if I call it as M dash, which is the product of new magnetic length, if I call it as 2L prime, and new pole strength as M prime, it happens to be 2L because magnetic length does not change and magnetic pole strength becomes halved. Therefore, magnetic moment of this will be equal to half the magnetic moment of the given magnet, given bar magnet. Now let us see the case when the given bar magnet happened to be cut into two identical pieces along its equatorial line. So as we discussed, the magnetic pole strength of each pole is M, and this is the midpoint of the magnet. So this is equatorial line. So we get two pieces. Each piece happen to have same area as that of the original magnet. Therefore, the pole strength of each piece will remain same as that of original if the magnetic pole strength of the original magnet is M. But as it is cut along the equatorial line, length of each piece will be half that of the original magnet. Assuming the original magnetic length is 2L, it is 2L by 2. It is also 2L by 2. Now, if I consider the magnetic moment of each piece now, it is pole strength remains same, but the magnetic length is halved. Therefore, magnetic moment of each piece is half of the magnetic moment of the original. Now, we can even talk about the cutting a magnet into so many pieces parallel to its axial line. Let us say you have a bar magnet of magnetic moment M, pole strength M, small m I mean to say. So pole strength is small m and magnetic moment is L. If it is cut into so many pieces, let us say identical pieces parallel to its axial line. Let us say it is cut into X identical pieces parallel to its axial line. As the area of each piece is 1/8 of the area of the original magnet, then we can say that the pole strength has become M by X if the original pole strength is M. But the length remains same as that of the original magnet. Therefore, new magnetic moment, if I call it as M prime, that is 2L, as the magnetic length remains same and pole strength is 1/8 of the pole strength of the original. Therefore, magnetic moment becomes 1/8 of the original magnetic moment. So similarly, we can talk about if the given bar magnet happen to be cut into Y pieces parallel to its equatorial line. If it is cut like this, 5 identical pieces parallel to its equatorial line. So as we discussed earlier, pole strength is directly proportional to area of the pole. It does not change here. So therefore, pole strength of the piece, each piece is same as that of the original, but magnetic length has become 2L by Y because we made it into Y pieces. Okay, here we made it into X pieces. Now, here the new magnetic moment can be given by, it is magnetic pole strength remains same M dash or M prime, and it is 2L by Y, it happened to be M by Y. Okay, like this we can talk about even the magnetized wire. If it is bent into an arc of a circle, if it is bent into V shape at the midpoint, etc., what happens to the magnetic moment of the new bent wire, we will discuss in the next classes.